Okay, so now this is an extra part out of the IB syllabus for the SL. But if you're really interested in trying to understand why we can have something like an NTC thermistor, then this is a explanation. I will try to keep it as simple as possible, but it also requires us to understand a little bit about the atomic structure. So if you have questions, just let me know, then we can go deeper into it, okay? But then I will assume that you can understand, like this is B and this is the boron, okay? This is an element that it has the Z equals to 5, okay? This is pretty good because it also helps us to review a little bit about topic E, right? Atomic structure. So Z equals to 5 means that at a neutral, as a neutral atom, it should have 5 protons in total and also like 5 electrons in total. So you can see here that it has actually the 2 layers of electron, okay? So it should have like 2 electron inside, okay? But here we just care about the valence electron, okay? So valence electron basically means that the electrons that localize on the outermost shell of the atom. So we have like 2 here, so that will be like 3 here, okay? So basically on the second layer they have 3 electrons. Good. Okay. The second elements that we really need to care about is the silicon. And for silicon, the Z is actually, let's see again. So what is the inside? Silicon. Silicon. I will double check it really quickly. It will be like 14. Okay. 14 is the Z. And actually, we don't really care about like the inner layers. We just care about the outermost shell, okay? And let's have like 4, okay? Just the outermost shell, just the valence electron. And then the last one we need to care about here is the phosphorus. Then we have the element sp. This is just like the inner core, and then outside here, the valence electron, there are 5 of them. 1, 2, 3, 4, 5. Okay. Another thing that you may need to know, that is the Author rule. Author rule, which means that in order for these atoms to be at a stable configuration, it should have like 8 electrons on the outermost shell, okay? So you can imagine like, okay, it's supposed to be like you have like 8 beds, you know, like 8 beds. I'm sorry, like you're supposed to have like 4 rooms, okay? 4 rooms there. And then in each room, you have like 2 beds, okay? For each electron to stay in. And they will have like 2 different spin ups or spin down. We don't have to really go into that deep, you know, but basically you can see that for this layer, it can contain up to 8 electrons to be a stable atom, okay? That's why it has the name octet rule, because oct just mean like 8, okay? That's the octet rule. Okay, so here for silicon, this is the structure, the lattice of silicon substance. So we have a silicon ally with each other like this, and then it will share, you know, it will share electron because it want to be fulfilled. So it have 4 already, it will share another electron. That is one. Let me try. Let's say if this is the silicon atom number 1, okay, of interest. So this is belong to the silicon. This is of the silicon, this is of the silicon, this is of the silicon. Of course, you can also like pick this one or this one or this one or this one. I just like choose this for randomly, okay? But I want to make sure that these two, like the 2 electrons in the same room, okay? And we just have like 1 of them. So that's why it will try to share the other electrons with the other atom around, like this one. So it will share one electron with silicon atom number 2. It will share another electron with the silicon number 3 here. It will share another electron with another silicon atom number 4 there. And it can also like share this electron with this silicon atom number 5 there. Does it make sense? Make sense, right? So like this electron will just like share one electron with on the 4 other silicon around it in order to get a stable configuration. Okay, so it just means that these electrons can have like 2 rooms to stay in. Okay, it's really fancy, right? It's just like, okay, you have a house from your mom, you have another house from your dad, so then you can have like 2 bedrooms on each house. Okay, and then you are a twin, then you need to stay together. We can see it like that. Okay, so what happened here? Here, this is not a pure substance which is on the silicon, but they will try to add just a little bit of portion of phosphorus to make it impure. But by doing this, the silicon usually, if you just have it like this, we don't have any free electron, right? Every electrons here, every babies here, every twin babies here, they're happy. They have like even 2 rooms to stay. They're happy with that. They stay stable in their room. But if you just add a phosphorus atom here, you see 1, 2, 3, 1, 2, 3, 4, 5. There are 5 of them. So actually, this is an extra electron. Okay, so for now, we can have a free electron, you see, because what? Here, 1, 2, 3, 4, 5, 6, 7, 8. Oh, no. There's just too many children in this house. They're not happy. So one of them have to be kicked out. Okay, we can see it that way. So that kick out one just become happy one because it's free now. So it will like travel, okay, across this lattice. Okay, so you can see that it just becomes something like this one. Okay, we got some free electron moving around. So that's why under the force of the voltage, then boom, it can move and then you got some current. So that's why for silicon, if you add some phosphorus here, it's become impure, then it can conduct electricity. But if just like by itself, then it's just an insulator. Okay, that's why we call this kind of thing is a semiconductor, because it's either a conductor and either also an insulator. And it's also only conduct with under some conditions. Okay, so basically here, when you have electron here, then it means that it's more negative, right? That's why it have like N type. This is an N type. Okay, this is an N type semiconductor. So what about this one? This one is another case. This one is boron. You add a little boron into the silicon. So now for the boron, it's just like 3 electrons on the outermost shell. So you can see here, we also know that there should be like A rooms for all the electron to live in, right? To move in. Oh, so opposite to this case, this one just have an extra. You see, it just have an extra hole in here for the electron to moving. So just imagine you have a lot of electrons around, right? Like this, sorry, let me put you this one. You can have this one here, or this one here, or this one here, or this one here. You have so many options, right? It's just that the twin here said, oh, I want to change to a new room. I want to move here to see if it's a better room. See, so they will keep moving, okay? But if this electrons moving here, then this one become a hole itself, right? And then another electron will be, oh, let's jump in there. The most nearest one will jump in here. So that's why instead of having like electron moving, you can see that this one is more like a hole moving, right? It's just like electron will keep jumping to this one, leaving another hole, and then we'll have another electron to fill in that hole. So conductor, semiconductor, works based on holes and electron. It's just not like as free electron as in metal. Sounds good? Okay, so I could say that the key word about the conducting for semiconductor is about the holes and also like free electron. Okay, that's the combination of both. I would recommend you to read the link will be in the comments below, so then you can explore more and deeper into this topic if you're interested in. And of course, if you want, just shoot me an email or just comment that and we can have more discussion about the semiconductor diet. But the things I want to emphasize here is just here, come back to this point. How can it become negative temperature coefficient? So basically, when they at a higher temperature, it also means that their energy is higher, right? Remember that, right? Temperature is a measure of the average energy. So it also means that the movement of those electrons here, of the holes here, will be, yes, faster. There will be more of them. So it's now this time at a higher temperature, we can see that the kinetic energy is more energy, and also like the gap, the gap between the conductant level and the insulating level and the conductant level, the gap has been like decreased because more energy as the temperature changing, increasing the thermal energy. So that's why for this kind of thing, at a higher temperature, you can see that there's a more movement of them. And if more movement of them, it means that more current, right? That will be because of less resistance. So that's why they can have the negative temperature coefficient. Does it make sense? Please let me know if something unclear. Okay? Thank you. Good luck.